students, friends and well-wishers. Here's another video on Newton's laws of motion. This is basically made for college physics students, but I guess it could be a starting point for anybody who wants to know and understand the laws of motion. There are 3 laws of motion, but before we get into that, I wanted to define dynamics, which actually gives the connection between forces and motion. Or it is the study of how forces create or stop motion. In fact, here is Newton's first law. An object at rest remains at rest, or if in motion, remains in motion at a constant velocity unless acted upon by a net external force. So now that shows 2 types of objects. One is an object at rest, the other is an object in motion. So an object which is at rest cannot move by itself, and an object which is in motion in a straight line with constant velocity cannot stop by itself. So for an object at rest to move, or an object that is moving to stop, there must be a net external force acting on the object. So that's what you mean by Newton's first law of motion. And directly from Newton's first law of motion, we get the idea of inertia. Inertia is the inability of an object at rest to start moving on its own, and for an object in motion to stop on its own. Now let's move on to Newton's second law. According to Newton's second law, net force is equal to mass times acceleration. So that means the greater the force, greater the acceleration. Remember that a force is measured in newtons when mass is in kilograms and acceleration is in meter per second squared. So Newton's second law always talks about the net force. That's what you got to be careful about. That means you got to look at all the forces acting on an object, find the total or the net force, and then set that equal to mass times acceleration. Weight of an object. Now, weight of an object is just the gravitational force on the object. So many people get confused between mass and weight. They are not the same. Mass is measured in kilograms, and weight is a force, so it's measured in newtons. So for example, if you have a mass of 1 kilogram, its weight is going to be 1 times 9.8 newtons. So if you have a mass of 2 kilograms, its weight is going to be 19.6 newtons. So weight is the force of gravity. That means if you take an object to another planet, its mass is not going to change, but its weight will change, since the acceleration due to gravity on different planets is different. So which means mass is a constant, weight changes from place to place. Newton's third law. According to Newton's third law, for every action, there is an equal and opposite reaction. Here it says, whenever one body exerts a force on a second body, the first body experiences a force that's equal in magnitude and opposite in direction to the force that it exerts. And I am trying to show that by means of a diagram here, where you have an object on a table, on a horizontal table. The weight of the object, in fact, the weight of any object acts vertically down. So m times g is the weight of the object acting vertically down. Since for every action, there has to be a reaction. The table pushes back up on the object, and that is called the normal reaction. It's called a normal reaction because that reaction is going to be perpendicular to the surface. So that is the normal reaction. So here I'm trying to say that the force on the table, which is B by the object, is mg. That's the action. But the force on the object, A, by the table is the normal reaction. So that means action and reaction do not act on the same object. They always act on two different objects. So that is Newton's third law. Next, we have to look at how to solve problems involving forces. And this is primarily done by drawing what is called a free body diagram. Now, what is a free body diagram? In a free body diagram, we isolate the object of interest, or we focus on the object of interest. And then we look at all the forces acting on the object of interest. Now look at this example. There are two persons pushing a third one. If the object of interest is the third person, we only look at the forces acting on the third person, which are the forces F1 and F2. We do not consider the reaction acting on the people who are pushing. We do not consider any of the forces. So that is called a free body diagram. Moving forward, I'm going to show you how we're going to apply the free body diagram. Take this example. The swimmer is trying to get a good start by pushing against the wall there. And our object of interest here, or the system of interest as shown, is the swimmer. So we're going to look at the forces acting on the swimmer. What are the forces acting on the swimmer? The swimmer is, first of all, pushing on the wall. Is that force acting on the swimmer? No. That force is acting on the wall, so we do not consider that force. But the reaction of that is acting on the swimmer. So that is why this force, which is the force by the wall on the feet, is shown. The other two forces are, of course, the weight of the swimmer, which is shown here, acting vertically down, and the buoyant force, which the liquid pushes up on. So those are the three forces there. Here is another example. In this example, there's an object. Actually, we looked at this before. There's an object on a table, and because it's heavy, you can see that the table is kind of sagging there, down there. So the two forces here are, one, the weight of the object acting on the table, and two, the normal force exerted by the table on the object. Since there is no acceleration along the y-axis, in fact nothing along either axis, we're going to say A is 0, which means that the net force, which is N minus W, is 0, so the net force is 0. Now we got to consider a more complicated motion where a skater is moving down an incline, as you can see. And look at the forces acting here. The weight of the skater acting vertically down, the normal force acting at right angles to the surface. Remember, that's why it's called the normal force. And then the third is the force of friction. I am just introducing friction here, but I want to tell you that friction always acts opposite to the motion. Now, since the person is trying to skate down or slide down, friction is going to be opposite to that motion. So those are the three forces in this situation. Now, to solve the problem, usually what we'll do is we will break this up into the components. Now, which one? But before we do that, take a look at how the x-axis is along the plane while the y-axis is perpendicular to it. So we have rotated the axis to make the x-axis along the plane and the y-axis perpendicular to the plane, which means the normal force is along the y-axis, friction is along the x-axis, but the weight of the person is neither along the x nor the y-axis. So that is why the weight is resolved into its components. And from this triangle here, we will get this component to be weight sine theta, and this component is going to be W cosine theta. So that is sine theta, and this is going to be cosine theta. So if the mass of the person is 50 kilograms, and then we know that the weight is 50 times 9.8, which gives 490 newtons. So that's the weight of the person. And now considering the net force along the x-axis, we know there are two forces along the x. One is this component W sine theta, the other is friction. Now the net force is one minus the other. But the net force must be equal to mass times acceleration, correct? Which means that you set this equal to mass times acceleration. So net force is mass times acceleration. Now imagine that there is no friction. If there is no friction, then this term just vanishes. So then we have W sine theta is equal to MA, and mg sine theta is equal to MA, and the masses get cancelled, and we get a very important result, namely that the acceleration of the object is g sine theta. Remember that this is true only when there is no friction. So if there is no friction, when an object slides down, its acceleration is going to be g sine theta. Does the acceleration depend on the mass of the object? No, not at all, because we saw that the mass got cancelled. So whether it's a light object or a heavy object, the acceleration is going to be g sine theta. For example, if theta is 30 degrees, then we're going to get g times sine 30, which will be 4.9 meter per second squared. Let me just write that quickly. This will be g times sine 30, which will give you 4.9 meter per second squared. Now we consider a situation where you have an object tied to a string and you are just holding it there. So as opposed to normal reaction on a solid surface, we will now call the reaction the tension. So now that means there are two forces acting on this object. One is its weight acting vertically down, and the other is the tension acting up. So let's consider that this object is just held there. So you're not moving it up, neither are you moving it down. So it's stationary. In this case, the net force, which is T minus the weight, must be equal to 0. Why 0? Because the acceleration is 0. You're not moving it, which shows us that the tension must be equal to the weight, which is mg. But in the second case, let's consider that you're actually moving the thing, you're holding it, but you're moving the object up with an acceleration a. So if you are moving it up with an acceleration a, then once again the forces are the same. The forces are tension and the weight. But this time you're not going to set, okay, that shows the acceleration. So this time you're going to say tension minus weight is MA. You cannot set it equal to 0 because there is an A. So now you pull this one to the other side, and that's mg, you know, weight is mg. So you get T is equal to ma plus mg. In the third case, let's consider that you're moving this object down with an acceleration a. Now you're moving it down. So the free body diagram is the same, but the tension is going to be different. In fact, in this case, the tension is going to be less. All right, so once again you have this, but look at the difference. The difference now, it's set to, net force is set to negative ma. Why negative m times a? Because you're going down, and down is negative. So when you rearrange that, you're going to get this. Weight is mg, so you're going to get mg minus a. So in the second case, the tension increases because it's ma plus mg. In the third case, when you're going down, the tension decreases. But I also want to show you something. I had added that as I was speaking. When you hold it stationary or you move it with a constant velocity, now I'm talking about constant velocity. In both of the cases, the tension will be equal to the weight. Let us work out a simple problem here. There is an object on a frictionless surface. It's acted upon by a force of 20 Newton. If the mass of the object is 2 kilograms, what is its acceleration? Well, that's very simple, because you're given the force, you're given the mass, and all you got to do is apply Newton's second law of motion. All right, those are the given quantities, and by the second law, net force is equal to mass times acceleration. Plug it into that, divide both sides by 2, and you get the acceleration of the object. So that's very simple. Remember that the unit of acceleration could also be Newton per kilogram. Newton per kilogram. Usually we use meter per second squared, but you could also have it as Newton per kilogram. Here's another one. Starting from rest, a 3 kilogram object reaches a speed of 10 meters per second in moving through a distance of 50 meters. What is the net force acting on the body or on the object? All right, once again, you're asked to find the net force, and the only formula you have is mass times acceleration. The mass of the object is already given, which means you got to find acceleration. So you go back into kinematics, and then you see that the initial velocity is 0, the final velocity is 10 meters per second, displacement is 50 meters. So we use those three and we find the acceleration. Once you get the acceleration, you just multiply it with the mass to find the net force acting on the object. So here are the quantities. The equation going to be used is this. Excuse me. And when you substitute the numbers and calculate, you get the acceleration as 1 meter per second squared. And then the net force is mass times acceleration, which gives you 3 kilogram times 1, which is 1 Newton. So that is where you tag back into kinematics, find the acceleration, and then find the net force. I hope that's clear. Finally, I want to talk about friction. Now, there are two types of friction. When an object is at rest on a surface, the friction is called static friction. But as soon as the object begins to move, the friction there between the two surfaces is now called kinetic friction. So there are two types of friction. Remember, friction always opposes motion. But if two objects are at rest relative to each other, it's static friction. Or static friction is the friction before motion begins. And kinetic friction is the friction after motion begins. And always remember that kinetic friction is less than static friction. And the two formulas are similar, except for the difference in the constant. So we have friction, static friction, given by mu s times n, where n is the normal force, and you have kinetic friction given by mu k times n. Now, these are the two constants. Mu s is called the coefficient of static friction, and mu k is called the coefficient of kinetic friction. And which one did I say was less? Kinetic friction is always less. N is the normal reaction or the normal force. So I'm going to illustrate how to work out a problem using these two formulas. Yep, mu k is less than mu s. Remember that. Here is a situation. There's an object of mass 10 kilogram kept on a surface, and at first we imagine that it's not moving, so you have the weight of the object and the normal force, and the weight is 10 times 9.8, which is 98 newtons, and the normal force in this case should also be 98 newtons. Why? Because the net force along the y-axis is 0. It's not moving up or down. So the normal force is equal to 98 newtons. If that is true, then the static friction given by this formula, mu s times n, can be easily calculated. Let's assume that mu s is 0.2. It'll be given to you, so it depends on the nature of the surfaces. Okay, so if mu s is 0.2, then what is the force of static friction? Then we get 0.2 times 98, which gives 19.6 newtons. So that's static friction. All right, so now consider that you want to move this object from the left to the right, so you're going to apply a force. Imagine that 25 newtons of force is applied, and now you're going to have kinetic friction exactly opposite. Okay? So in this situation, we got to look at the net force along the x-axis now. So you have two forces. One is 25 newtons, and the other is the friction. Those are the only two forces acting along the x-axis. Therefore, when you consider the net force, and also let's take mu k to be 0.15, because mu k has to be less than mu s, right? Can you find the acceleration? So that's the thing. When you apply that force, what is the acceleration of the system? Okay, to find that, consider the net force along the x-axis. What is the net force? It's 25 minus Fk. Why minus? Because friction is opposite. And this net force must be equal to mass times acceleration along the x. Therefore, 25 minus friction, kinetic friction, should be equal to mass times A. I'm just saying A instead of AX. Do we know kinetic friction? Yes, we know. It's given by mu k times n. Mu k is 0.15 and n is 98. So from those two numbers, you get kinetic friction as 14.7 newtons. So take that and plug it in here into this equation. And then the mass of the object is 10 kilogram. So 10 times A. And then solve that equation. And you would get the acceleration. In this case, the acceleration is going to be slightly over 1. It's 1.03 meter per second squared. So that's how you do problems involving friction. I hope you understood this. I've just tried to produce this video as quickly as possible to give you fundamental ideas. Now please add on to these ideas by reading your textbook and then try to submit the homework. Thank you and God bless.